The next talk, there is a changement for organization motivations, is Professor Giorgio Valle from Venezuela.
If we try to see gravity at very small scales, well, we can, because we don't have any quantum gravity. When we say gravity at very small scales, what is the same gravity at very high energies, but we don't have any consistent quantum gravity, not yet. However, there are some theories which pretend to say something about quantum gravity. The famous superstrings theory, a beautiful extra-dimensional theory, M theory, supergravity. Maybe n equal 8 supergravity is consistent quantum gravity. We don't know yet. And recently, Horava gravity. However, Horava gravity has some problems. So most of these theories are supersymmetric theories. And supersymmetrics is not just a beautiful and elegant theory. It works, and works very well. However, what experimental data says is that we don't have supersymmetry, not yet. So that is a problem. I work on supergravity, so I know very well what supersymmetry means for people working on high energy physics. That is a big problem. So everything is becoming more and more complicated. So maybe it's time to search for some new theory. But why we want to describe gravity at very high energy? Well, because we have many processes at very high energies. For instance, we want to know what happened with gravity around this Big Bang. So we want to see its consequence in our observable universe. Maybe the dark energy problem has to do with the fact that we don't know what happened with gravity at very high energy. This is the standard cosmological picture, but we don't know what happened with gravity around the Big Bang. And also, we have many astrophysical processes at very high energy, the gravitational collapse, black holes, neutron star, quark star. We don't know what happened inside very compact distributions. We need quantum gravity to say something about this. Of course, we can use general relativity, but if we want to see what happened with gravity at very high energy, which are processed in collapse, in gravitational collapse, we can't say anything. So the motivation for this is, well, our final idea is to try to say something about this fundamental problem, dark energy and dark matter. And in this particular talk, what we're going to do is to try to say something about astrophysics in an extra dimension, in particular in the brain-world theory. The brain-world theory is a 5-dimensional theory. Well, there is more than 5-dimensional theories, but in this particular talk, we are going to talk about astrophysics in the brain world, 5-dimensional brain world, and try to see something about what happened with Einstein field equation, with correction from Einstein field equation, and try to see the astrophysics consequence about this. So we're going to show some preliminary results about this extra dimension consequence on compact stellar structures. Okay, the brain world, it's a very nice theory. According to this theory, we live in this hypersurface, 3+1, and we have an extra dimension, so we have 3+1+1. The main characteristic of this theory is that the standard model is trapped in the brain, the hypersurface. the extra dimension. So what we are going to do is to consider Einstein field equation, 5-dimensional Einstein field equation, and we're going to project Einstein field equation on the brain. And we're going to see the astrophysics consequence of all this. Okay, finally some technical details. We start from Einstein field equation in 5 dimensions, the book, and let's go to 3 + 1, the brain. Now we have Einstein field equation with some modification. This modification can be seen here in the energy momentum tensor, which now has new terms. These new terms are the high energy corrections and no local correction. This parameter is the brain tension, which is a very important parameter because when sigma goes to infinite, we must recover general relativity. Now, the high energy correction are written by this way in terms of quadratic terms in the energy momentum tensor, which is new because in general relativity we don't have any quadratic terms in the material field. And the no local correction can be written by this way, an scalar, an anisotropic term, and energy flux. In our case, well, we are going to consider static distribution, so the energy flux will be 0. So the only 5-dimensional fields we are going to work with is this one, this scalar, and this anisotropy. This is the projection of the 5-dimensional tensor on the brain. Okay. So we have an open problem here. This open problem has to do with the fact that the brain-wave equation is not a closed system. And the source of this problem is this non-local correction. This is the problem. This is the source of the problem. So many ways were taken to solve this open problem. The simplest one is, well, if this is the source of the problem, the simplest solution would be take this constraint, but this is incorrect. Many papers were written about this constraint, but finally people realized that this is incorrect because it's not consistent with Bianchi identities. The other constraint people usually take is this one, but this is too strong because 5-dimensional effect produce some anisotropy in 3 + 1, so this is too strong. And actually it's incorrect too. We realized about this some times ago. Okay, what we are going to do is to try to see what happens inside a very compact distribution. Using this theory, okay? So the simplest solution is the vacuum solution. So we have spherical symmetric and static solution, and we have a vacuum solution for this point. We say vacuum solution because actually it's no vacuum. Okay, there is no density, there is no pressure. However, we have 5-dimensional fields. So it's not a real vacuum. But anyway, this is the simplest solution. It's a kind, okay, this M is the mass of the distribution, a Q is a 5-dimensional effect, the tidal chart. So this is the simplest generalization to the famous Schwarzschild solution. The other very famous solution is the Casadio solution, Casadio-Fabry and Mazzacurati solution. Again, M is the mass of the distribution, N is M is the mass of the distribution, and eta is a free parameter which measures deviation from Schwarzschild solution. The main difference between these two solutions is the fact that the dark radiation here is 0. So we are going to use this fact as a useful tool to see what is the role played by these two 5-dimensional effects on any compact distribution. Okay, so let's start for, let's consider a simple distribution, density and pressure, perfect fluid. We are going to see what happens inside distribution, in this context, in the brain world context, now we have high energy terms because we have high energy correction to Einstein field equation. So now everything is too complicated, too complicated. But even worse, when we consider five-dimensional effect, we have a serious problem because there is no solution for this problem. The system of equation in the brain is not closed. So we have to prescribe some kind of information. Now the problem is what kind of information we are going to describe. What is the logical information we need to prescribe here? Well, there is no solution, but actually we found a general effective four-dimensional solution for this problem. And that is the target of this talk. Now, Einstein field equation with high energy correction, we have a static spherical symmetric distribution. We have two geometric functions, nu, lambda, and two material fields, density and pressure. So we have four unknown functions, and we have 1, 2, 3, and 4 equations. No problem with high energy correction. But we must consider no local corrections. And now we have an indefinite system. Now, what is the constraint we have to consider to solve this problem? Well, it's hard to say. The same Einstein equation rewritten by a different way, we can see that this solution is written in terms of the standard general relativistic solution plus some corrections. Now, we can see that we have only one equation to obtain three unknown functions. So clearly the system is not closed. So we have to try to find some kind of solution here. Now, the idea actually is very, very easy, and it works, and works very well. Let's see this solution. This solution is general relativistic solution plus corrections, high energy correction and no local correction. But actually, this is not a solution because the dark this VI function, this scalar function, actually depends of the geometric functions. We can see that this dark radiation depends on the geometry, and the geometry has a very complicated expression. So actually, what we have is an integral differential equation. This is a very complicated problem. So what is the solution for this? The idea is very simple. We consider general relativity plus some geometric deformation. What does it mean? Well, five-dimensional produce some kind of deformation in 4 dimensions. So the idea is to consider standard general relativity plus deformation due to 5-dimensional effects. And we need to find this deformation to try to say something about this system. Of course, this deformation produces some anisotropy inside the compact distribution. And after some calculation, we found that this deformation has this expression, a very complicated expression. We can see high energy corrections and this one. Now, all this must be consistent with general relativity, the low energy limit. When we take this limit, the only way to ensure general relativity is to impose these constraints. This is a natural constraint. So this constraint has a very clear interpretations. If we see the constraint, the constraint has high energy correction plus some very complicated expression. We can eliminate this high energy correction because a compact distribution always has density and pressure. So the only way to ensure general relativity is to impose in this constraint, but this remain. So this is the minimal deformation approach. This is the minimal deformation or minimal anisotropy projected onto the brain. This is a very clear physical interpretation for this. Now, we have 4 equations, Einstein field equation, plus a new additional equation, this constraint. So for no uniform distribution, the constraint is not enough, as the system remains indefinite. But in the case of a uniform distribution, this constraint, this very natural constraint, closes the problem. So, okay, let's see what happened with uniform distribution. This is the famous Schwarzschild solution. Let's consider the Schwarzschild internal solution, and let's see what happened inside the distribution. We're going to obtain the Schwarzschild solution in blue plus some deformation on red. Okay, after some very complicated calculation, we obtain this expression. Always in general relativity, in the astrophysics context, we have an internal solution and an external solution. We have to match both solutions. When we match both solutions, we obtain the constant. I mean, we obtain this constant here. B and C are constant, which are going to be found by matching condition, okay? So finally, we obtain something very interesting. Sorry. This is a qualitative graphic for 3 different distributions. This is the more compact distribution. So we can see that more compact distribution undergoes a higher anisotropic effect. This happens in any kind of general relativistic solution, not only for uniform distribution, okay? And the Weyl function is always negative, always, in any kind of distribution. The physical interpretation for this is very clear because by Einstein field equation, we can see that this Weyl function can be written by this way. This term is always negative. These are high energy correction, and this is an anisotropic terms. So the fact that this is always negative means that these terms, the high energy correction, dominate on these anisotropic terms. It's a very clear interpretation. Now, what happened with no uniform distributions? Because in the case of no uniform distribution, the system remains indefinite. But what is amazing here is that this constraint works for every kind of general relativistic solution and works very well. I mean, any general relativistic solution satisfies this constraint. So this is a natural way to obtain any brain-world version for any general relativistic solution. It's a very natural way. Okay, let's consider now a no uniform distribution, a more realistic situation. This solution is a very no solution, density depression, and this geometric function. It's a solution for a perfect fluid. So we use this approach, and finally, we're going to obtain an exact solution for these 2 Weyl functions. So it's amazing because we have a physically relevant solution, but it's an exact solution. What happened with work effect, with 5-dimensional effect? Because this is a general relativistic solution, but where is the 5-dimensional effect on the density or the 5-dimensional effect on the pressure? Well, the 5-dimensional effect can be found by matching condition. When we use the matching condition, for instance, for the Martin solution, the exterior Martin solution, we are able to obtain these constants, and it works very well. So finally, we are going to be able to see the role of this two functions, the dark radiation and the dark pressure, okay? This is general relativity. This is general relativity. And we have two different exterior solutions. The Casadio solution, which is this one, and Martin solution, which is this one. The main difference between these two solutions is the dark radiation. But it was an open problem because nobody knows exactly what happened with dark radiation and dark pressure. What is the effect on compact stellar structure? And this is very clear because it's clear that in this case, with no dark radiation, the pressure is reduced by 5-dimensional effect. So that means that the exterior dark radiation always increases both the pressure and the compactness of the stellar structures. And of course, for the dark pressure always reduces this. In this solution, we have no dark radiation, only dark pressure, and the pressure was reduced by 5-dimensional effects. So this is a very interesting and very important solution in the context of 5-dimensional brain world, in the astrophysics context, of course. Now, finally, the conclusion. The minimal geometric deformation approach represents a natural way to see the 5-dimensional consequence on compact distributions. Both exterior Weyl functions, that is the dark radiation and dark pressure, have well-defined consequence on stellar structures. The exterior dark radiation always increases both the pressure and the compactness of the stellar structures, and that the exterior dark pressure always reduces them. Now, an exterior solution without dark radiation and with dark pressure surrounding a stellar distribution might be seen as an environment with physical effects on the stellar structure are such that it can be considered as a region with negative effective pressure. That is a kind of dark energy surrounding a compact distributions. Okay, that is.
Discussion, please. This is very interesting topics for sure. Congratulations, very elaborate calculations that you have done, indeed.
Thank you for your very nice presentation. Can you please go to slide 49? Slide 49, excuse me, I said, slide 49, my apology. I wasn't being very clear. 49. I'm going to ask something very simple, not extended. All right. All right. You say in the case of non-uniform distributions, the constraint, which you have right there, is not enough to close the system of equations. However, any general relativistic solution satisfies the condition. Okay. Now, that's what you said for slide 49. Go to slide 58, please. Yes. Yes. Okay, you're talking about closing the system. Okay, as you said, you can't close the system, but you still can satisfy the equations that you want. Okay, so you look at the very first one right over there about would you be able to close the system with that type of set of assumptions, or?
Any general relativistic solution satisfies that.
Use the microphone, please, so we can all hear you. Sorry.
Any general relativistic solution satisfies this constraint. So what we have done here is pick up a general relativistic solution and use this minimal geometric deformation approach. So what we found was the brainwave's version of this general relativistic solution, because that constraint, h equals 0, is satisfied for every general relativistic solution. So all we have to do is to pick up a general relativistic solution, and by this method, we're going to obtain a consistent brainwave version. When I say consistent brainwave version, what I mean is a solution which has the correct low energy limit, and that is general relativity. This problem is complicated. It's very complicated because we have no linear terms in the material field.
Thank you very much.
You're welcome.
Question, please. Yes. Stay. I'll bring it over. No, stay.
Okay. With respect to this kind of theory, from my point of view, is very nice, but it describes only steady states in an evolution equation. Evolution equation means the metric depends on mass, partial derivative of the metric with respect to the mass equal Einstein tensor. Like Hamilton flows in differential geometry in 82, scientists from America, differential geometer, introduced this kind of evolution, taking the metric depending on time, derivative of the metric with respect to time equal minus 2 Ricci tensor. And he discovered that it's possible to use such kind of evolution in order to obtain stronger results about the manifold. So here, in my opinion, instead of time is a mass, so you take the derivative of the metric with respect to the mass equal Einstein tensor. And in this kind of theory, your solutions are steady states. So perhaps more complicated evolution can be described using this kind of equation. I don't know, because I have in my notices, I explained to the students, but I haven't written a paper till now in this subject.
The open problem here is the 5-dimensional problem. There is no solution yet for 5-dimensional.
Microphone. Speak to the microphone, please.
Hello. There is not 5-dimensional solution for this problem, not yet. It's an open problem. So all we can do is take the effective 4-dimensional equation. But that doesn't mean that any physically consistent 4-dimensional solution is a good solution for 5-dimensional solution, because we don't know the 5-dimensional solution. Nobody knows that. It's an open problem.
Any other question, please? I'm sure no other question. I have a question. This is an issue I ask myself many times. Of course, I do not have the answer. Maybe you see, the 3+1 structure of space-time is due to our sensory perception. We have 3 lobal Eustachian lobes and the sense of time. What is your feeling regarding the possibility, which is realistic, that the universe, the real world is more than 3+1 dimension? What is your gut feelings?
Well, for instance, maybe it's easier to speak about superstring theory.
But that's superstrings.
Well, okay. In this case,
something more
it's different.
concrete, less formal, more concrete.
Well, in this case, is.
I mean, I don't deny. Sorry if I interrupt you. Superstring theory are a beautiful theory. I'm not criticizing them. Only I will appreciate more concrete. Sorry for the interruption.
Yes, in this case, in the brainwave theory, we have only one. Well, in the 5th dimension, we have one extra dimension.
Sure.
Okay.
Oh, sure.
So, but the standard model is trapped in 3+1.
Yes.
So we can, for instance, we can send a photon to the extra dimension. We can build any experimental, yes, there is no experimental way to reach this extra dimension by an electromagnetic way, because the photon can reach
Yes,
the
I
fifth dimension.
agree.
Only gravity.
Yes.
But gravity is too weak. So the only way to see this extra dimension is by a gravitational way. Now, so what is the way to see this extra dimension? Well, the way is try to see deviation from Newton potentials. The Newton potentials, if you are able to see deviation
Oh, yes.
from Newton potential, you are going to be able to see something about these extra dimensions.
Yes, yes.
Because in this case, this modification to Newton equation occur only at very high energy.
Yes.
For large scale, you are going to recover Newton theory. So the only way to see this is by
high energy, yes.
gravitation.
Still, I would like to stimulate you to think about some experiment that, because it will be big, if there is some more concrete and possibly low energy way of testing the another dimension. This will be something really big. Yes, so I wish you discover this way. Gentlemen, if you are agreed, we have authorization from the top level to have a 5 minutes break, and then you have a coffee at the coffee. You know, there is a coffee shop in the square here around the corner. It's hard to see, but if just go at the end of the square and on the left, and you will see the nice presentation. Thank you. Yes.